Yes, it is spicy. Give me one second. I'm going to mute y'all. All right, Zoomies, can you hear me? Awesome.
Yes.
Yes, it was a very spicy conversation. The two classmates in here were trying to convince me that we shouldn't have a final exam. And then question was asked about whether or not it could be a majority decision. And so. All right. Because this is last day of the semester, technology is going to continue to give me a little pain in the tuchus. All right, let's try round whatever we're on. Cool. All right, so today is your last statistics lecture until you all go into grad school and have to take statistics again. So I know you all are sad to be done learning statistics, but as my little gift to you, today what we're going to be learning, you won't be required to calculate anything. So these will just be concepts I am introducing. Amber, don't look too happy. Oh, it will be on the exam, but you're just not going to, you have to calculate it. Yeah. All right. But before we do, what did we learn last time? Kind of, sort of, not yet, quite. Binomial. Yes. So binomial test, yes. So a bimodal distribution would be a distribution that has two modes, right? And so the binomial test is looking at what? What are we looking at? Okay. Give me more high level and then we'll get into the P and Q. Why would we ever run a binomial test? Yep, so we use z-scores. Yes, we're doing a test that has two distinct categories. So somebody give me an example of the type of research question we would use a binomial test on. Yes, so we talked about the visual cliff example last class. Somebody come up with a new example that we haven't talked about. We talked about that too. Yep.
Multiple choice answer?
So not multiple choice, because multiple choice tends to be more than two options. So it could be like true, false, as long as it is a dichotomous choice, right? There are two categories. And what type of data? Frequency, is it nominal? Yeah, so we're using categorical frequencies, right? And so in this case, it's not really ratio data that we're looking at the frequencies of the counts. We also learned about the sign test, right? And so when would we use the sign test?
Like when people are sick and if they've gotten better or worse?
Yeah, so we're using a sign test if we're just looking at better or worse. And in what environment, like what context, why would we prefer that to getting specific quantification? Like what are some of the limitations that allow us to run a sign test?
Like a limit, like if it doesn't have a limit, you can use it?
Exactly, the whole Mean Girls example, the limit does not exist. Yes, perfect. All right, questions about what we learned last time?
I had a question about, so are there two different equations that we use for the regular binomial test and the sign test to find Z?
No. So as I mentioned in class last time, that was a typo in the slides. The slides have been updated and re-uploaded. And so,
Okay.
yeah, so that is just,
Sorry about that.
that's the equation. Other questions?
Got it.
All right. Your last fun fact of the day. While in graduate school, astrophysicist Neil deGrasse Tyson considered becoming a stripper to earn extra money. He visited a club and watched dancers perform to the song Great Balls of Fire and left immediately and became a math tutor instead. Yeah, how different would life have been potentially? All right. So in chapter 20, 4 different statistical techniques are introduced. Yes, that's 2 baddies. To deal with ordinal data, right? And that is to say, data where the measurement procedure simply arranges the subjects into an order. And we talked about doing a Spearman correlation based off of ordinal data earlier this semester. Looks like somebody's mic is still on and they're kind of rustling around here. It's not showing up who it is, but if your mic is on, if you can go ahead and mute yourself, so I don't have to mute the whole class. So the statistical methods presented in this chapter can be used when the original data consists of ordinal measurements, or it comes from an interval ratio scale, and we convert them to ranks, because they don't satisfy the assumptions of that standard parametric test that we use, like a t-statistic. And so what are those standards that we have to satisfy if we're going to be using a standard parametric statistic, like a t-test or an ANOVA?
It has to be a bell curve.
Yeah, so it has to be a normal distribution, exactly. Yeah, so we're making assumptions about the distribution of data, right? Because everything is going to be essentially an odds ratio, and we have to know roughly what percentage of people are going to fall within plus or minus 1 standard deviation of the mean. Perfect. So those 4 statistical tests include the Mann-Whitney test that evaluates between 2 treatments or 2 populations using data from an independent measures design, which is to say 2 separate samples. So what parametric equivalent is there to the Mann-Whitney test?
Like an ANOVA?
Well, you could, I guess, in theory, do an ANOVA, but this is a substitute because it has 2 treatments or 2 populations. It's a t-test. And what kind of t-test?
Independent t-test?
Yes, exactly. Independent measures t-test, right? So if you would normally run an independent measures t-test and you violate the assumptions of skew or kurtosis, right? So the data is not normally distributed. You would run a Mann-Whitney test. The Wilcoxon test evaluates the difference between 2 treatment conditions using data from a repeated measures design. So again, that is the same sample is tested and measured in both treatment conditions. So what would be the parametric equivalent of the Wilcoxon test? Yeah, a repeated measures t-test. Or sometimes called a dependent t-test. The Kruskal-Wallis test evaluates the differences between 3 or more treatments or populations using a separate sample for each treatment condition. And so what would be the parametric equivalent for the Kruskal-Wallis test? One way ANOVA, yes. And the final test, the Friedman, evaluates the differences between 3 or more treatments for studies using the same group of participants in all the treatments. So what would be the parametric equivalent of the Friedman test? Yes, exactly. Repeated measures ANOVA. All right, so let's dive into them a little bit here. The Mann-Whitney U Test, like we just mentioned, can be viewed as an alternative to the independent measures t-test. So you would be using the Mann-Whitney test if you had a sample that was pulled from a population that has a non-normal distribution. We would also typically use the Mann-Whitney test if you had less than about 15 people in each condition. Right? We haven't done that for the semester, but as you move forward in your statistical careers, you know that there's a baseline number of subjects we have to collect. And if we don't have that, we're violating some of the assumptions of these parametric statistics. And so in that case, you may want to use a Mann-Whitney U test. The test uses the data from 2 separate samples. The test for a significant difference between 2 treatments or 2 populations. The Mann-Whitney test only requires that you're able to rank the individual scores. Thus, you don't need to compute means or variances. So null hypothesis for the Mann-Whitney U is just like the null hypothesis for the parametric independent measures t-test, which says that there's no systematic or consistent difference between the 2 treatment populations being compared. So you can see here what we do is take every one of these values, right? And so, you know, this may be group 1, this may be group 2, and we put them in ascending order and then just rank their placement, right? So this person gets rank 1, rank 2, rank 3, rank 4, etc. And so you can start to see a differentiation in the groups, right? So here, just looking at it, you can see that treatment A seems to have an effect when compared to treatment B, right? Now, looking at this, what is something that comes to mind as another reason why you may want to be using this Mann-Whitney U based off of data you have? Give you a hint. It's another reason why we use the sign test. But what if
You have to use it when data has no limit? Is that
yes,
where you're going?
well, so it has to be a relative limit, but you're kind of on the right track of, you know, what if participants 17 and 18 in this case had values way outside the norm, right? So we're talking about, let's say, you know, blood pressure medication, and we have treatment A, which could be the actual blood pressure remedy, and treatment B would just be the placebo. Well, maybe participants 17 and 18 have astronomically high blood pressure, and we don't want to exclude them, but if we keep them in the traditional mean comparison, like we do with the independent measures t-test, their data could make it look like there was an effect, even if there was no effect. All right, and so it helps guard against some of those extreme outliers having a significant impact. And what you see down here on the bottom is a little bit more of a nuanced picture, right? There's not a clear differentiation or separation between the data like you have above. So again, it doesn't tell you the distance between 1 and 2, or 9 and 10, 16, 17, etc. But it just provides that rank ordering. So again, I'm not going to have you calculate this, but I think it does help to learn about the process. The calculation for the Mann-Whitney U statistic requires that you combine the two samples and rank order the individuals in that combined group. So you have 15 in each group. Now you put them all together, line them up, smallest to largest, and then rank order them, 1 to 30. Once you've established that rank order, you compute the Mann-Whitney by either finding the sum of the ranks for each of the original samples and use the formula to compute a U statistic for each sample. Or you can compute a score for each sample by viewing the ranked data as if they were, oh, hey, McAfee. As if they were finishing positions in a race. Each subject in sample A receives 1 point for every individual from sample B that he or she beats. The total number of points is the U statistic for sample A, in the same way a U statistic is computed for sample B. I like this because it almost gamifies the whole process. You find yourself rooting for one of the groups. The Mann-Whitney U is the smaller of the two U statistics computed for the sample. If there's consistent difference between the two treatments, the two samples should be distributed at opposite ends of the rank ordering. In this case, the final U value should be small, and at the extreme, when there's no overlap between the two samples, you'll obtain a U of 0. Thus, a small value for Mann-Whitney U indicates difference between the treatments. Not a beer. What is Miller Lite? Oh, no. No, this is LaCroix because I'm fancy and because it was on sale. To determine whether the obtained U is sufficiently small to be significant, you go look it up in the table. For large samples, that obtained U statistic can be converted to a z-score. And the critical region can be determined using the unit normal table. All right, questions about the Mann-Whitney U?
Why do we go with a lower U?
Yeah, so let's, I'm just gonna draw over this. So let's say we had 10 participants, and let me just draw 10 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now let me go ahead and fill them in. So we have 5 for condition A and 5 for condition B. If there is, to the extreme, this big of a difference, such that all for condition A fall on one side and all for condition B fall on the other side, what you do is evaluate how many for condition A at each point beat, how many of condition B are beaten by each for condition A, right? And so this beats 5 for condition B, this beats 5 for condition B, 5 for condition B, 5 for condition B, 5 for condition B, right? And now, for each of these B, you look at how many for condition A it beats. Well, this beats 0, this beats 0, this beats 0, this beats 0, and this beats 0. Right? And so you add them up for each treatment condition. So 25 and 0, and then you take the smaller of the two. So I would take 0 in this case. Right? And so, in this case, wherein we have clear differentiation between the two groups. Condition B is never going to have any one beat any of the other. But now, let's say, I'm just going to draw these as ends because it's easier for me to do. 5, 6, 7, 8, 9, 10. So now, let's say there is a lot of cross-representation here. You can see that for this first A, that beats 5. For the second A, that beats 4. That beats 3. That beats 2. That beats 1. This beats 4. This beats 3. This beats 2. This beats 1. This beats 0. And now we add all of them up for A and B, and it's going to be a larger number, right? And so you can see that the more kind of intermingled they are, the larger the number is going to be for both sides. And if you're taking the smaller version or the smaller answer for both sides, the smaller is still going to be a relatively large number, which corresponds to this kind of intermixing there. Does that make sense?
That makes sense. Thank you. And you always do the smaller number so it's consistent.
Yes, exactly.
Okay, thank you.
Other questions? Yeah.
When this might be so tell me if it is, but when would you use this over just a t-test? If you have 10 people with heights, why would you take the time to rank an order instead of just taking heights from you samples?
Yeah, so let's say we were interested in, you know, the heights of people from 2 different cities, right? And so let's pull from Breckenridge, Colorado, and from Huntsville, Alabama, right? And you want to see if there is a difference as a function of the altitude they grew up on, right? Because there's actually evidence to suggest that the higher altitude you grow up, you're smaller, and so we want to take a look at that. If we get somebody from Huntsville, Alabama, who's 7.5 feet tall, that's going to throw off our data if we've got such a small sample size like that. And so it would benefit us to still account for, okay, the average heights as a function of rank there, but we don't want that person who's 7.5 feet tall to distort the rest of our data. Does that make sense? Cool. Other questions?
So in that case, you'd have the one from the shorter sample all the way on the taller side, but the rest of them would still be clumped.
I'm sorry, say that one more time.
The Huntsville, the
Mhm.
taller, the taller one.
Yeah.
You said the super tall one was from Huntsville.
Yeah. Mm-hmm.
So it still wouldn't matter the difference. It would just be that they are significantly taller.
Yeah, so every person is essentially counts as 1 point, right? So there's no biasing of the data as a function of having extreme outliers. Good question.
I'm kind
Right,
of
so we go-
confused. Can you do another example real quick? I don't really understand what you just did, really.
Yeah,
I'm sorry.
all right. No, that's totally fine. So let's say at the beginning of the semester, I said that the average salary of a geology major at UNC in the 1990s was something like $120,000, right? And we came to the conclusion that that was because Michael Jordan was a geology major at UNC and was making stupid amounts of money every year. And so we decided that using a median was a better means of describing that data than was using the mean. And so with this sort of test, we're essentially doing the same thing, right? And so let's say we wanted to compare the different majors at, I swear to God, if McAfee comes up one more time. We wanted to compare the different majors at UNC in that case. It wouldn't necessarily make sense for us. Let's say we're comparing geology and business. It wouldn't make sense for us to do the typical t-test, right? Because the t-test is looking at the mean differences. And so if you've already established that the mean is not a good measure for describing that group of geology majors at UNC, it doesn't then make sense to use the mean in our statistical test, right? And so in that case, you know, we're going to rank order them such that, you know, geology major, business major, geology major, business major, and then geology major, right? And so if we were to look at just the mean, so, you know, let's say this was 40,000, this was 41, this was 48, 49, 50, 52, 72, and then you have Michael Jordan up here who's making 100 million. If we were to just do the mean comparisons, Michael Jordan up here making 100 million really distorts that value. But if we do it as a rank order, now we can see, okay, well, Michael Jordan clearly wins, and we're still going to account for his score up here, but now he only counts as essentially one block, right? One participant. And so now we can make the comparison, and what we find is that, okay, business majors seem to actually be making more, even though we're still accounting for Michael Jordan. We're not throwing out his data. But business majors tend to make more money than do geology majors. Does that make sense?
Yes, that makes sense. Thank you.
Of course. All right, let's go ahead and move on here. So the Wilcoxon T test, as we already talked about, is an alternative to the repeated measures T test, using data from one sample where each individual has been observed in 2 different treatment conditions to test for a significant difference between the 2 treatments. As with the Mann-Whitney U, there's no need to compute a mean or variance for those different scores. All we have to do is, once again, rank order. Null hypothesis, as you would predict, simply states there's no systematic or consistent difference between the 2 treatments being compared. We'll come back to that. So to calculate the Wilcoxon T statistic, you first observe the difference between treatment 1 and treatment 2 for each subject. You then rank the absolute value of those differences. So again, we're not taking the positive and negative. We're ranking from closest to 0 all the way up to furthest away from 0. Then find the sum of the ranks for positive differences and the sum of the rank for the negative differences. And that Wilcoxon T is the smaller of those two sums. All right, and so what you can see, let's just ignore column A here. We have 5 participants, and ignore what they're looking at. But we'll take time 1 score minus time 2 score. And here are their different scores. So for participant A, their time 2 score was 4 points higher. For participant 2, their time 2 score was 14 points lower, etc. And then we rank order them as a function of distance from 0. Again, we're looking at the absolute value, not the sign. So -1 is only 1 from 0, gets 1. 4 is 4 from 0, gets 2. -6 is 6 from 0, gets 3. 9 is 9 from 0, gets 4. And 14 is 14 from 0, gets 5. If there's consistent difference between the two treatments, the different scores should be consistently positive or consistently negative. And at the extreme, all the differences will be in the same direction. And one of those two sums will be 0, right? If we have no negative directions of change, right? No negative differences, summing all of the negative difference ranks will just be 0, right? Because we have none of them. Thus, as with the Mann-Whitney U, a small value for T indicates difference between treatments. Because you all aren't sick enough yet of tables in the back of the book to figure out whether it's significant, you got to consult that Wilcoxon table. And as with the Mann-Whitney U, for large samples, the obtained T statistic can be converted into a z-score, and the critical region can be determined using the unit normal table. Question about the Wilcoxon T test.
So it's something we still need to like calculate. We're just not doing any problems in class. Is that what you mean?
So you won't have to calculate it for the final exam. Like I will ask you questions about these, but I'm not going to give you data and tell you to compute these.
Okay, so we just need to understand more conceptually. Okay, I understand it.
Cool.
Like maybe questions about whether the Wilcoxon test is like equivalent to the repeated measures. Those are the type of questions.
Yeah, that type of thing. Or, you know, what type of what type of data are you feeding into this Wilcoxon test, right? And this book, I swear to God, John McAfee. Okay, then I have to go through the system, yeah, and fix that. Yeah, so knowing things like, you know, you first have to rank order the data, right? And so it's not just pure numerical values.
I see. Okay.
And this is why you all should become statisticians, because if you come up with a better statistical way of doing things, you could name it like the Williams Q test or whatever you want. See? There you go. The Kruskal-Wallis test, as we talked about, is an alternative to a single factor, independent measures ANOVA. The test uses data from 3 or more separate samples to evaluate differences among 3 or more treatment conditions. Once again, you're rank ordering, and it doesn't require numerical scores. And as you would expect, the null hypothesis for the Kruskal-Wallis simply states there are no systematic or consistent differences among the treatments being compared. So how do you do this? Combine the individuals from all the separate samples, one big group, and you rank order that entire group. So if you have 20 people in each of the 3 treatment conditions, you're now rank ordering from 1 to 60. So another example of a type of question that may be on your final exam would be something like, if you have 3 samples of 20 people each and performing a Kruskal-Wallis, do you rank order each from 1 to 20 or the whole thing from 1 to 60? The answer is the whole thing from 1 to 60. You then regroup the individuals into their original samples and compute the sum of the ranks for each sample. To compute the Kruskal-Wallis, you use a formula, essentially a chi-square statistic with degrees of freedom equal to the number of samples minus 1. So k minus 1. The obtained value must be greater than the critical value for chi-square to reject the null and conclude that there are significant differences among treatments. So again, we have our original data here. We combine all of them together, and then we rank order them. You then put the corresponding ranks back into their columns, and you'll calculate from there. So when you sum up each of these columns, right, this is the sum of those ranks. And then you would plug them into the formula. But again, because you're not calculating it, don't worry about it. Questions about this? All right. And the final test, the Friedman test, can be viewed as an alternative to that single factor repeated measures ANOVA. As with repeated measures ANOVA, you're using data from one sample to evaluate differences among 3 or more treatment conditions. Rank order the individuals again. And that null hypothesis is just as you would expect. There are no systematic or consistent differences among the treatments being compared. You first rank each individual or the individual scores across the treatment condition. The sum of ranks then computed for each treatment. Formula is then used to compute the Friedman test, which is just distributed as chi-squared statistic with degrees of freedom equal to the number of treatments minus 1, so k minus 1 again. And that obtained value must be greater than the critical value for pi square with that set degree of freedom, or degrees of freedom, to reject the null and conclude that there are significant differences among the treatments. So unlike before, where we combined them into one big group and then rank order that big group, what we're doing is assigning a rank for each participant across the different treatment conditions. So for person A, their smallest value was placebo, so they get 1 in placebo. Their second smallest was drug A, so they get a 2 in drug A. Their third smallest was drug B, they got a 3 in drug B. And their highest was drug C, so they get a 4 in drug C. For participant C, their first smallest was drug A, so they get a 1 for drug A. Their second smallest was placebo, so they get a 2 for that. They get a 3 for their third smallest for drug B, and they get a 4 for drug C. You're then adding them up by column, the rank orders. And then plugging it in. All right, questions about the Friedman test? Awesome. All right. So, couple quick things about your final exam. For your final exam, should have to know how to perform independent samples t-test, dependent samples t-test, one-way ANOVA, repeated measures ANOVA, two-factor ANOVA, correlation regression, and chi-squared. You should be able to know the difference between mean, median, and mode. Know the difference between an ANOVA and a t-test. Know the difference between parametric and non-parametric statistics. So in addition to what we covered today, what is another non-parametric statistic we covered this semester?
Chi-square?
Yeah, chi-square, exactly. You should know how to interpret a regression equation. You should also know how to interpret an effect size. So if I tell you that a certain effect has an R squared of 0.50, what does that conceptually mean? So not R, we're talking R squared. So R squared would be that effect size. Yeah. Oh, sorry, that wasn't a hand. Yeah. Yeah, so 50% of the variance in one variable can be explained by that other variable. Exactly. What questions do we have? This isn't the study time, but what questions do we have about the final exam? I'm not promising I won't, but you've only got a fair amount of time for the final exam, and all things considered, that doesn't seem that important to me. So, be passively familiar with it, but you're not going to fail the exam if you don't study it.
If you didn't test us on it in the previous exams, is it still going to show up on the final?
Yes.
Okay.
Will there be any definitions on the final?
No more so than what you see here, right? You may be required to essentially provide definitions for mean, median, mode in your presentation as to what the differences are. You know, knowing conceptually why you would use a non-parametric test is kind of definitional. But like, I'm not going to say, what is the definition of ANOVA?
Okay, thank you.
Mm-hmm. 435 questions. No. I don't know how many questions it'll be. You'll be able to finish it in time, so don't worry about it. And then, no, this one is 250 points. So this one is weighted an extra 25%. I am dropping the lowest test grade. I don't remember. Probably. It's in the syllabus. So But yes, and I know this question will come up before or after the final exam. And also, let me say, before the final exam, everybody has to take the final exam. You don't get to drop the final exam. If you don't show up for the final exam, you're going to be missing 250 points in your final grade calculation. Another question that will come up is, well, I did really poorly on my final exam, so can I just not drop one of my earlier exams? No, right? The maximum number of points you can get for the first exams is 400 points, right? So me not dropping one of your grades only brings down that average and only hurts you. So the highest of your first two exams will be counted, as will your final exam. Yes? If somebody didn't get 100, yep.
You guys don't get 100. Nobody gets 100. I'm talking to you smarties out there. I know you know who you are.
For those of y'all who are not familiar with game theory, this is a classic example of game theory. Go look it up tonight and then go look up the Nash equilibrium. This is a classic example wherein it does not benefit you to put weight into the idea that anybody will hold out from getting 100. Well, probably won't. All right, what other questions do you have about the final?
Is the best way to study to do the practice problems?
To do the practice problems and more practice problems, yes. Yeah, practice, 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 practice. Yeah, Andrew. So on Monday and Wednesday after Thanksgiving, we'll have review sessions. So during class time on Monday and Wednesday, we will have review sessions. Come with specific questions. I don't want to re-lecture about a concept only because I don't think it's fair to the rest of your classmates if we spend an entire class going over a concept. So come with specific questions and we can address them as needed. If other questions come up in your studying, feel free to shoot me an email. We can set up a Zoom meeting. I don't think they're doing the tutoring blitz this year. Is it? Well,
They are.
we're
I think
essentially
it's
doing
just going
that.
to be online.
Yeah, so we're essentially doing that with the week after Thanksgiving. So, anything else?
Are classes happening like school-wide, or is that just up to professors?
So classes, you mean like that week after Thanksgiving? Technically, that is still the school year. So I'm just doing it as a review session because I do that every semester, but.
I forget what happened the last 2 semesters, which is kind of embarrassing. But was there a study week, like a whole week of no class before finals?
No, there was class, yeah, after Thanksgiving, so.
I remember like last semester specifically because everything like just happened with all this. All the teachers were trying to figure out what to do. So some teachers.
Thanksgiving is a study week.
Yeah, exactly. No time off. Exactly. All right. Well, if there is nothing else, have a lovely weekend, a lovely Thanksgiving. Be safe. Just because, you know, if you die in your week of Thanksgiving, you still have to take the final exam. So, Ace shrugged it off. He doesn't care. I think she believes in ghosts. Yeah. Exactly.
When you play Among Us and you die, you have to be a ghost in your house.
You still got to do. Well, I have the rest of the I have unfinished business. I have to take